Go ahead.
So it is my great pleasure to have the opportunity to introduce Anthony Christiana to you, who is working on his PhD thesis under supervision of Józef Przytycki at George Washington University. And Anthony is going to present to us some of his recent results together with co-authors on introducing homology to quasigroups. So please, Anthony, start.
Thank you so much, Anna. Thank you to the organizers for the opportunity to speak. This work came about after a happy visit from Anna to our George Washington knot theory group. So it's a sort of strange bedfellows here of universal algebra and homology theory. So back in spring of last year, Anna brought us this paper by Phillips and Wojciechowski, classifying varieties of Bol-Moufang Quasigroups, and our idea to define a homology theory for Bol-Moufang Quasigroups sort of grew from there. Okay, so this is joint work with Anna, as I said, and then my advisor, Józef Przytycki, two other of his full-time students, Ben Klingenpiel and Huisheng Guo, Ali Guo, and another visitor that we had, Jin-Seok Oh from Kyungpook University. Okay, and so like I said, our goal is to define some homology theory for this strange class of algebras called quasigroups. And so all of the structure of this talk is contained right here in this title. First, I'll tell you what quasigroups are. Then I'll tell you what it means for quasigroups to be Bol-Moufang type. And then I'll show you how to define a homology theory, what motivated this definition, and I'll try and convince you why this is the correct homology theory to define in this case. Okay, so if you want to scroll through our paper, there it is. And if you want to scroll through the Phillips and Wojciechowski paper, which was a major motivating example, there it is. All right, so beginning with quasigroups. Okay, so I'll give you a few equivalent definitions of quasigroups. But first, I'll lay out the map of magmas. So in the most natural way, I think to a magma, a set with a closed binary operation, we would start by adding the axiom of associativity and get a semigroup. And from there, we might decide to add an identity next for a monoid. And if we add in our inverse elements, we end up with a group. But quasigroups are actually magmas with a different choice of starting axiom, and that axiom is divisibility. And so magmas with divisibility, which I'll define precisely in just a second, are quasigroups. If we add identity elements to quasigroups, we get the class of algebras called loops. And to get back to groups, we need to add our associativity. Okay, so if you're familiar with something of the homology theory of associative structures, you know that that semigroups have a very well-defined homology theory, well-studied. Usually it's presented as a cohomology theory, and therefore so do groups. And so, like I said, our work today is defining homology theory for this class, quasigroups. Let me pull up my notes here. Okay, a few equivalent definitions for quasigroups, which I'll call QG. Oops. Quasigroups. So this is from the perspective of universal algebra. I guess first I'm going to use this word a lot, variety. So maybe I'll define variety first. And by variety in this talk, I mean a class of all algebras satisfying a given set of identities. Okay, so not varieties in the algebraic geometry sense, but just algebras with some imposed identities. So in this perspective, what are quasigroups? The variety of quasigroups are the universal algebras they are sets Q with three operations: multiplication, a sense of left division, a sense of right division. And they have the property, okay, all of these operations need to play nicely with each other. So starting off with, if I left multiply an element B times A, I can then left divide by A to get back B. Similarly, if I right multiply, right divide, I get back B. And then in the opposite direction, I can left divide, left multiply, and okay, I can right divide, right multiply. So I'll present a definition that's a little bit more intuitive, but for now, this is essentially what it means to have divisibility on your magma, right? There's a unique solution. So this is equivalent to saying that this operation AB, A left dividing B, is the unique solution to this equation AX equals B. So that's divisibility on a magma. All right, an alternate definition of quasigroups is that these are magmas with two maps: left multiplication x goes to A times x, and right multiplication where these left and right multiplications are bijections. Okay, so magmas with left and right multiplication being bijections is another way to define quasigroups. Something that we have immediately is, if you want to play with these things, is that there's always the cancellation property in quasigroups. So AX equals AY implies X equals Y. That's actually if and only if. And maybe a third equivalent definition is that the Cayley tables, the multiplication tables for quasigroups, are exactly Latin squares. Okay, so if you're looking for an example of a quasigroup, you can just look at any Sudoku puzzle. So Sudoku puzzle, and that'll tell you a quasigroup. Okay, I know some Sudoku puzzles. The first one is Z mod 3. Okay, 0, 1, 2, 0, 1, 2. Okay, Z mod 3 is definitely a group. If I go back to this little lattice here, the adding axioms goes in one direction. In the opposite direction, we have subset inclusion, right? So every group is a quasi-group, every group is a loop, every group is a semi-group. And so certainly all groups, including Z mod 3, are quasi-groups. How about a quasi-group that's not a group? I'm going to label my elements by 0, 1, and 2 again, but that's sort of arbitrary. I don't function like 0, 1, and 2. Here is a multiplication table for a quasi-group, which is not a group. So this is A is not a group. And we can see that for one by the fact that there's no identity element here. No left multiplication map is the trivial permutation. Okay. So that's what it means to be a quasi-group. Now, this class of quasi-groups that we were especially interested in were Bol-Moufang Quasigroups. The names are from two mathematicians, German mathematician Ruth Moufang. I don't know if I'm saying that right. Ruth Moufang, who was writing about these structures in 1935, and Gerrit Bol, Dutch mathematician, writing about these structures in 1937. And essentially, Bol-Moufang quasigroups are quasigroups with an added identity, an added equational relation. And that equational relation is in some way meant to approximate associativity. Okay, so these, so loosely, these are quasigroups with an added identity which approximates associativity. Okay, so non-associative structures, but we want to get sort of close to associativity. Let's just see that, okay, associativity is something that's non-trivial here. So in A, let's see the example that this structure is not associative. How about the word 0 times 2 times 1? And that same word parenthesized a different way. Okay. The structure I'm telling you is not associative, so I'm expecting something different. Here's a 2, here's a 1, result is 0. So this is 0 times 0, and 0 times 0 in A is 0. On the left, 0 and 2 is 1, and 1 times 1 is 1. So, okay, I've received two different answers. My quasi-group's not associative. What are these added identities which are supposed to approximate associativity? They are called Bol-Moufang quasigroup identities. And they're built in the following way. Okay, they'll be named Vij, where V is one of the following 6 letters, corresponding to an underlying word for your equation. So we'll build, as an example, B4, 5. So we'll set up an equation. On both sides of this equation, we'll have the word B. So X, Y, X, Z, X, Y, X, Z. And I and J are choices of parenthesization, according to this dictionary. So for 4, 5, what are we looking at? On the left, I will use parenthesization 4. On the right, I'll use parenthesization 5. And so this is my Bol-Moufang quasigroup identity B4, 5. Okay. So, like I said, one motivating paper for this work was the paper by Phillips and Wojciechowski. I'll just abbreviate Phillips and Wojciechowski because I have a picture of it. And I also have a chart here. And what is this chart telling me? Okay, so Phillips and Wojciechowski did the work of classifying varieties of Bol-Moufang quasigroups according to which variety a given identity induces. So what is that to say? That's to say that sometimes, for instance, B4-5 quasigroups, all quasigroups that satisfy this axiom, actually turns out to be also the set of D2-4 quasigroups. So you could pick as your defining relation for this variety, either B4-5 or D2-4, and you'll receive the same class of quasigroups. In this case, this class of quasigroups has a name, and they're called flexible quasigroups. And various varieties have names or have been given names in this paper by Phillips and Wojciechowski, depending on how widely they were studied before in the past. Okay, so this chart that we're looking at here tells us which defining Bol-Moufang quasigroup identities define the same variety of quasigroups. So here's my example of flexible quasigroups, which can be equivalently defined by B4-5, D2-4, and E1-2. Okay, so maybe I'll build D2-4 as well. D2-4, so I take as my underlying word X, Y, Z, X, D2-4, X, Y, Z, X. And 2-4 is right parenthesization, left parenthesization. Okay. D2-4 is like that. Okay, so we'll call these two Bol-Moufang quasigroup identities equivalent because they define the same variety of quasigroups. I'm also happy to stop for questions at any time. All right. Maybe something else that we should take note of in this chart here is that this variety of quasigroups up at the top is actually just the variety of groups. And we see that there are 22 equational identities, Bol-Moufang quasigroup identities, which define associativity. So it's at least believable that all of these Bol-Moufang quasigroup identities approximate associativity. In fact, some of them are equivalent to associativity. Okay, right. And how many, and maybe I'll just also say how many Bol-Moufang quasigroup identities are there? Well, I have 6 choices of word. I have 5 choices of my first parenthesization, 4 choices of my second. It doesn't matter if I put my, swap the order of the expressions over the equal sign. And so I have 60 Bol-Moufang quasigroup identities, but Phillips and Wojciechowski show that there are only 26 varieties pictured here. Okay. With some understanding of what Bol-Moufang quasigroups are, we now look to define a homology theory.
I'm sorry, just one question
Yeah,
again.
please.
Yeah. So the Bol-Moufang quasigroups, do they have to have identities? No, right?
No,
No.
yeah,
So
not in
just
general.
some of these equations imply the existence of an identity, and
Yes.
that's how they end up in that top group. Just so I understand. Okay.
Um,
Or well, no, that's not exactly how they end up, but that's one thing that would have to happen if they ended up in the group box, I guess, right?
yes. Well, I think there's another one of these that's specifically for loops. So in fact, the answer to this question is no. If you have an identity, you can partition these in one way. So you're partitioning loops by these Bol-Moufang quasigroup identities. And if you have a quasigroup, you're partitioning in another related way. So, right, I guess this is sort of misleading here because these are not necessarily groups; these are associative quasigroups. But if we have an identity, then all of these identities define groups. Yeah.
Okay. All right. Thank you.
Thank you. Okay. All right. So now I'm defining a homology theory for these things. So we'll take as our example our sort of motivating homology theory for a given universal algebra, group homology. And if you're familiar with group homology, that's great. If you're not, no worries. This is just for intuition. In group homology, okay, so for any homology theory, we need a chain complex, a sequence of abelian groups or modules, and some boundary maps between those chain modules. Okay, so we need a chain complex, meaning that we need that this boundary map n between Cn and Cn minus 1 has the property that applying the map twice yields 0. Okay, so with any chain complex, we define a homology theory by the kernel of the nth map and the image of the n plus 1th map, n plus 1st map. In the case of group homology, which we'll mimic pretty closely, we take as our chain modules n-fold copies, n tuples in a group X. So for X, a group, our chain module is going to be just free abelian group free module generated by copies of elements in X. And I won't define what these boundary maps are for group homology, but I will show, for instance, the proof that the D2 map applied after the D3 map is 0. This would mean that we have, in fact, a chain complex. And you can mostly let your eyes glaze over this mess of expressions, except I want you to notice that we have, after composition, just one non-trivial canceling pair. And that non-trivial canceling pair cancels if and only if associativity holds. Okay, so the idea here is that we leverage the extra equational identity, in this case it's just associativity, to make some boundary maps that rely on this equational identity to cancel to 0. All right, so that's the idea that we want to mimic in quasigroups. Where does so in the case of quasigroups, we will take free modules over this polynomial ring in T and S, and we'll just take, again, tuples in X. So this is for X, a quasigroup. And we'll define a boundary map 2 on x and y by this map tx plus sy minus xy. This product here is happening inside of our quasigroup. And our goal now is to define some third boundary map, the boundary map 3, respecting Bol-Moufang quasigroup identity Vij. So we'll put in a little bit of work to do this, but essentially we hope to spit out a boundary map that relies on our definition of this identity Vij and uses that identity Vij in order to cancel after composition. Okay. And a note about future directions, right, is that we've actually only built this chain complex as far as our degree 3 chain module, right? So this will be our D3 Vij. Here's our D2, and here's our D1 map, which is just the 0 map. And so a future direction, right, is actually to extend this homology theory up into higher dimensions. All right, but for now, our goal, as I said, is to define this boundary map 3 respecting Bol-Moufang quasigroup identity Vij. I'm going to hide some details here, but I want some intuition. For our choice of these maps. So what led us to our guess? And this is actually a technique that we are following from Eilenberg. And the technique has to do with extensions by affine quasigroups. Okay, so our guess is informed by extensions by affine quasigroups. What are affine quasigroups? They are abelian groups A with 2 automorphisms, some T and some S, and a chosen, think of it as a scalar, C0. On this abelian group, we'll define a new operation star, which spits out a linear sum of elements in our abelian group A. And this has a quasigroup structure, and this quasigroup A star is said to be affine over our abelian group A. Okay. What will we do? I said we're going to define some sort of extension. What are we extending? We're extending a quasigroup X. In our case, this quasigroup will be our Bol-Moufang quasigroup. We'll take some affine quasigroup, and we want to define a product structure. We want to define a quasigroup structure on the product A times X. To do so, we'll define this map phi from pairs in X to A. This function is called a 2 cochain. And we define an extension of X by A. Okay, this is the quasigroup on pairs, as I said. And it has this sort of nasty looking formula. Okay, this A times B operation is happening in my affine quasigroup A. This XY operation is happening in my Bol-Moufang quasigroup X. And this is my 2 cochain from up top. Essentially what Eilenberg does is that by imposing a Bol-Moufang identity on this new extended quasigroup, A times X, we get back some conditions for our 2 cochain. And after some linearization, that allows us to guess we guess D3 for a given identity. Okay. But I've mostly waved my hands. I just want to say that the process for guessing these boundary maps is by extensions by affine quasigroups. But the way that we'll build these in practice is actually completely visual and relies on invariance of rooted binary trees. Okay. So it's 4 now. So this is definition of a boundary map 3 for Vij based on invariance of rooted binary trees. Okay, what rooted binary trees are we talking about? We'll think of every Bol-Moufang quasigroup identity as a set of 2 trees, and we'll call those trees T of B4, T of B5. As we remember, every number here from 1 to 5 corresponds to a parenthesization. And so all parenthesizations are Catalan objects, which means they're in bijection with rooted binary trees, also some Catalan objects. So this tree will be the rooted binary tree corresponding to 4. In this case, this tree. And we will decorate the leaves of this tree according to the word B. Okay, so all I've done is just realize 1/2 of my Bol-Moufang identity as a tree with some decorations. Similarly, we'll do so for 5. 5 looks like everything bunched to the left. And it's again decorated by the underlying word B. Okay, so these are our rooted binary trees. Now I'll define an invariant Q on these rooted binary trees. So given a tree T, we'll define an invariant Q, which is a sum over all of the vertices in our tree, except for the leaves. Each term will have a coefficient h of v. This h of v is just some monomial, some polynomial in this polynomial ring with t and s variables. And it'll have some tuple g of v, which is going to be defined recursively, but is a tuple in my quasigroup X, in tuples in my quasigroup X. Yeah. Okay. And once I define H and G, my identity Vij will turn into a boundary map 3, by taking Q of T of Vi and subtracting Q of T of Vj. So I'm reinterpreting all of these extensions by affine quasigroup technology into invariants of rooted binary trees. Now I just need to tell you how to build H and how to build G. So H of V for a vertex is just a monomial, which in T and S, which tells me how many left turns did I take as I travel from the root vertex to my vertex V. And S tells me how many rights I took. Okay, so for a given tree, here's my vertex V. H of V will just be one left, one right, so TS. All right, how about G of V? G of V is defined recursively. If your vertex V is a branch for two leaves, so 2 degree 1 vertices, then G of V is just the pair of those leaves. If instead one of the children of V is itself a branch, what you'll do is we'll find G of V for this branch here. Okay, so I'm going to label these X, Y, and Z. So here's G of V for this vertex. Maybe I'll call it V1. G of V2, well, its right component is a leaf, so it'll just be Z. But since its left component is a branch, it'll be the product of that tuple. So it'll be X, Y. Okay. All right, so this Q thing defines a polynomial, defines a word in my chain module C2, which we'll recall is Z of TS with pairs in X. And why don't we build this for B45? Okay. So B45. B45 looks like X, Y, X, Z. This is the tree corresponding to underlying word B and parenthesization 4. I have 1, 2, 3 vertices here. So I'll evaluate V1, V2, V3, Q of T of B4. All right, I'm summing over all of these pairs. So H of V1, tells me how many lefts or rights do I take from my root vertex. So 1 left, 1 right. So H of V1 will just be T times S. And G of V1, my pair in X, will be just Y X, since both of its children are leaves. How about V2? I took 1 left to get there. My left child is a leaf. My right child is a branch, so I multiply. And for my root vertex, it is my root vertex, so I have no monomial out front. And on my left, I have X, Y, Z. Right, I have, oops, X, Y, X. space here. X, Y, X, and Z. Okay. We could do the same process for this other tree, T of B5, and we'll spit out another polynomial, another linear combination, T squared XY plus T of XY, X plus XY, X, Z. And finally, we now have a boundary map B45, which tells me what to do with a triple XYZ. I should just take the difference of these two invariants. Okay. So a major part of our work was just this reinterpretation step, this seeing extensions by affine quasigroups as invariants of rooted binary trees. And in fact, this perspective helped us eventually solve what's written as a conjecture in the paper, which is that the Bol-Moufang Quasigroup homology theory detects actually the variety and is not dependent on the defining relation. I'll talk a little bit more about that in a second. For now, what I'll show you is an example. Here is a table, a quasigroup. We've computed a bunch of, so this quasigroup satisfies a variety of axioms, a variety of Bol-Moufang quasigroup identities, including this one, F14, E14, B14. And for different choices of my automorphisms, T and S, I can get back some different homology. In this example, so two choices of T and S produced different homology groups. But now, essentially, we've defined H2 given a Bol-Moufang quasigroup identity. But this is, at this point, still a little bit unsatisfying because our homology group H2 of some Bol-Moufang quasigroup satisfying an identity Vij with the choice of automorphisms T and S depends on Vij. Okay. What does this mean? This means that even though, for instance, for flexible quasigroups, I could take either B45 or D24 as my defining relation. I'm not yet sure if these homology groups would be the same, even though these identities are equivalent. They define the same variety. Okay, so in our paper, it's actually stated as a conjecture, but I've since proven the result that what this homology theory does is truly pick apart it does detect the relevant information, the variety, and not the identity. Okay, so I'll state that formally, but first, maybe I'll just record what we've built so far. So for every relation Vij, and for a quasigroup X satisfying Vij, we define our chain groups to be these free abelian groups over tuples in X. We define our third boundary map with respect to this Bol-Moufang identity to be the difference of these rooted binary trees under this invariant Q. We define our second boundary map to just be this scaled, tx plus sy minus x times y. And right, we have that for all identities, this really is a chain complex. And as in the group case, the proof, the fact that D2 after D3 of Vij equals 0 depends on the identity Vij. Meaning if there are some non-trivial canceling terms in this composition, but those non-trivial canceling terms are exactly our Bol-Moufang quasigroup identity. Right? So this extensions by affine quasigroups technology gave us the right guess. Okay. Now to go back to what I was saying before. We've defined second homology groups in terms of a given identity, but because we know that some identities, say B45 and D24, define the same variety, it would be sort of lackluster if their homologies groups H2s were different for equivalent identities. So this is a conjecture in our paper, but since has been proven. So we showed that this is, in fact, I would say this justifies the fact that this is the right choice of homology theory. So if I have two Bol-Moufang quasigroup identities which define the same variety, then my second homology groups that I've built are in fact equal. Okay, and so for example, for my original example that I showed you of a quasigroup, it was a quasigroup that was not a group. I had this Cayley table, 0, 2, 1, 2, 1, 0, and 1, 0, 2. So this is in fact a flexible quasigroup. And so if I hit this with a homology from a flexible defining relation B45, it is in fact the same as hitting it with any other defining relation. And in this case, it happens to be 3 copies of Z and some Z2 torsion. Okay, how am I doing on time? All right, and so maybe I'll finish by giving a brief sense of how this proof might go to show that these two, that any two equivalent relations define the same second homology group. And it comes back to this picture here. So notice that in order to say that H2 of some Vij is equal to H2 of some WKL, I know that I'm taking a kernel of a D2 map that doesn't depend on a relation, kernel of a D2 map that doesn't depend on a relation, and I'm quotienting by the images of some D3 maps which do. So proving that these are equivalent is enough to show that these two images are the same. How will we do that? We'll see that any two Bol-Moufang quasigroup identities which define the same relation are linked by some intermediate identities. And the way to get from one identity to another intermediate identity will be either cancellation, which is always allowed in a quasigroup, or substitution, which is allowed in any magma. And essentially that cancellation and substitution induce isomorphisms on the images of these invariants Q for the relevant trees. So we induce isomorphisms on the images of our boundary maps with respect to some relation when canceling and substituting. And so we have some long string of isomorphic images. In this case, we just have 3. And this is not too hard to see if you're able to track how the trees are changing and the resultant change on these invariants Q. Okay, so cancellation and substitution induce isomorphisms on images. So as far as future directions, there's a lot to be done here. I think that Bol-Moufang quasigroup identities are interesting as sort of near associativity, but can we define homology theories for any given equational identity? So some sort of unified theory of homologies for universal algebras. And like I said, in particular, we are looking to extend our construction to higher degrees. So what is H3 of some Bol-Moufang quasigroup with a given relation? Okay. And I think that's all I want to say. Thank you so much for the opportunity to speak. I really appreciate it.
All right, thank you. Thank you. Any questions?
I have a question in terms of like involvement of say this combinatorial objects. By the way, it's like one excellent talk. It's very interesting how the penetration of combinatorics happens in universal algebra, because when you're dealing with some combinatorics of identities, right? Like how exactly like you're grouping symbols and having your variables on both sides, and yeah, wonderful. So this looks like really is an excellent combination, right, of different approaches of seeing varieties. But the question is, like, you heavily use this famous Catalan objects, right? Like these binary trees. What do you think, like, for your future, like if you're extending it to the higher level, will you be able to kind of extend this usage of combinatorics, and which exactly objects you
Yeah,
foresee like for your attack of new hypothesis, right?
yeah, absolutely. I think that any universal homology theory for some universal algebra is going to depend. Well, I think the best way to approach it will be with these rooted binary trees. And this invariance proof uses the cutting and I guess the opposite of cutting, like grafting of these rooted binary trees really heavily. Um, uh, like like in the case of groups, right? There's only there are only two trees. What's interesting about these Bol-Moufang quasigroups is that they're counted by C2 number of trees. What's interesting about these Bol-Moufang quasigroups, right? They're counted by C5. They have somehow like too many variables. That's why it's so hard to define a boundary map for. But I think that understanding, the combinatorics of these trees will be the key to defining higher homology theories. But yeah, this is very sort of introductory work in this direction. Thank you for the question, though. Yeah.
Thank you.
Other questions? Oh, all right. If not, I'll stop the recording and let's thank the speaker again.
Thank you.
All right.